Now, in this lecture, we'll answer on two questions. In the first question, we'll find out the value of line segment DE that is equal to x. In the second question, we'll find out the value of the shaded area that is inside the quarter circle. So we'll start with the first question. In the drawing, we have triangle ABC. We know that angle ABC, this angle equals to 30 degrees. Angle ACB, this angle also equals to 30 degrees. And we also know that this angle DAE, equals to 60 degrees. And line segment BD equals to 5 units, and line segment EC equals to 4 units. And our mission is to find out the length of line segment DE that is equal to x. Okay, so we focus on triangle ABC. In triangle ABC, those two angles are equal to each other. They are both equal to 30 degrees. So I write it down. In triangle ABC, angle ABC, this angle equals to this angle that is actually angle ACB, and both angles are equal to 30 degrees, therefore they are equal to each other. Okay, I repeat again. In triangle ABC, angle ABC equals to angle ACB. They are both equal to 30 degrees, therefore they are equal to each other. And we have the rule that in front of equal angles in the triangle, there are equal sides. So in front of those two equal angles, there are equal sides. In front of this angle, we have side AC. In front of this angle, we have side AB. And according to the rule that I mentioned, side AB equals to side AC. Okay, so for the fact that those two angles are equal to each other, we conclude, according to the rule that I mentioned, that side AB equals to side AC. Okay, here side AB equals to side AC. Okay, and we also know that the sum of the angles in any triangle is equal to 180 degrees. So here we define angle ABD as alpha, and we define angle EAC as beta. And according to the rule that the sum of the angles in any triangle is equal to 180 degrees, so especially the sum of the angles in triangle ABC must be equal to 180 degrees. So which angles we have in triangle ABC? We have this angle that is equal to 30 degrees, plus this angle that is also equal to 30 degrees, plus this angle that is equal to alpha according to our definition, plus this angle that is equal to 60 degrees according to what is given in the question, and plus this angle that is equal to beta according to our definition. So in total, the sum of those angles must be equal to 180 degrees. So here this equation states that the sum of the angles in triangle ABC is equal to 180 degrees. Okay, so here we have 30 degrees plus 30 degrees is 60 degrees, and 60 degrees plus 60 degrees is 120 degrees. We have here also plus alpha plus beta, and in the other side of the equation we have 180 degrees. So we found out that 120 degrees plus alpha plus beta equals to 180 degrees. Here we subtract 120 degrees from this equation, and we get that alpha plus beta equals to 180 degrees minus 120 degrees, it is 60 degrees. So we found out that alpha plus beta equals to 60 degrees. Okay, so in the next step we will do two constructions. In the first construction, from point A, we will draw a straight line in such a way that the angle between the straight line and side AC will be equal to alpha. So here, this angle equals to alpha according to our construction. And we will do also a second construction. From point C, we will draw a straight line in such a way that the angle between the straight line and side AC will be equal to 30 degrees. So this angle equals to 30 degrees according to our construction. In the next step, we will extend the straight lines until they intersect with each other. And we will define the intersection point of the two straight lines as point F. Point F is the intersection point between those two straight lines. So here we created a triangle ACF. So in the next step we will prove that the new triangle that we created, that is triangle ACF, is congruent to this triangle, triangle ABD. Okay? So we'll actually prove that this triangle, triangle ABD, is congruent to this triangle, triangle AFC. So why those two triangles can go into each other? First of all, those two angles, they are both equal to alpha, therefore they are equal to each other. So I write down that angle, this angle, that is actually angle BAD, is equal to this angle, that is actually angle CAF. So both angles are equal to alpha, therefore they are equal to each other. Here, I repeat again. Angle BAD equals to angle ACF, both angles are equal to alpha, therefore they are equal to each other. In addition, we have already proved that side AB equals to side AC. So I write it down, side AB equals to side AC. Repeat again. We already proved that side AB equals to side AC. And finally, those two angles, they are both equals to 30 degrees, therefore they are equal to each other. So this angle is actually angle ABD, and it is equal to this angle that is actually angle ACF. Both angles are equal to 30 degrees, therefore they are equal to each other. I'll repeat again. Angle ABD equals to angle ACF. Both angles are equal to 30 degrees, therefore they are equal to each other. So actually, we proved the triangle ABD is congruent. This is the sign of congruent to triangle AFC. According to angle side angle rule. I will explain what I mean here. Those two angles and the side that attach to those two angles, that is side AB in this triangle, triangle ABD, are correspondingly congruent to those two angles and the sides that attach to those two angles, that is side AC in triangle AFC. Therefore, those two triangles can go into each other according to angle side angle rule. And from the fact that those two triangles can go into each other, we will derive two things. First of all, that side BD equals to side FC. So I write it down. BD equals to FC. I repeat again, side BD equals to side FC. According to the rule that corresponding sides in congruent triangles are equal to each other. Those two triangles can go into each other, therefore the two corresponding sides, that is to say BD and FC, must be also equal to each other. But according to what is given us in the question, side BD equals to 5 units. So we can write here that BD equals to 5 units. And for this equation, 5 equals to BD equals to FC, we derive that FC is also equals to 5 units. Okay, side FC is also equals to 5 units. And the second thing that we will derive from the fact that those two triangles can go into each other is that side AD is equal to side AF. AD equals to AF. I repeat again, side AD equals to side AF according to the rule that corresponding sides in congruent triangles are equal to each other. So if we define side AD as A, here side AD equals to A according to our definition, then from this equation A equals to AD equals to AF, we derive that side AF is also equals to A. Side AF is also equals to A units. In the next step, we will join points E and F together by a straight line. And we will prove that the green triangle, triangle ADE, is congruent to the orange triangle, triangle AEF. But first of all, we have already proved that alpha plus beta equals to 60 degrees. Therefore, this angle FAE, that is equal to alpha plus beta, it is actually equals to 60 degrees in size. So, we will prove that those two triangles can go into each other. So why the green triangle is congruent to the orange triangle? First of all, we just right now proved that those two sides are equal to each other. That is to say, side AD equals to side AF, and they are both equal to A according to our definition. I'll repeat again. Side AD equals to side AF, and they are both equal to A according to our definition. In addition, those two angles, they are both equal to 60 degrees, therefore they are equal to each other. So angle DAE in the green triangle is equal to angle EAF in the orange triangle. They are both equal to 60 degrees, therefore they are equal to each other. I'll repeat again. Angle DAE equals to angle EAF, and they are both equal to 60 degrees, therefore they are equal to each other. And finally, this side, side AE, is a common side that belongs to both triangles, therefore this side equals to itself. So side AE equals to side AE. It's a common side that belongs to both triangles. Repeat again, side AE equals to side AE. It is a common side that belongs to both triangles. So we actually proved that the green triangle, triangle ADE, triangle ADE is congruent to the orange triangle, triangle AEF. According to side angle side rule. Okay. Here I explain what I mean. Here, those two sides and the angle that is included between those two sides in the green triangle are corresponding congruent to those two sides and the angle that is included between those two sides in the orange triangle. Therefore, the green triangle is congruent to the orange triangle according to side angle side rule. And from the fact that those two triangles can go into each other, we'll conclude that side DE equals to side EF. I'll repeat again. From the fact that the green triangle is congruent to the orange triangle, we will conclude that side DE equals to side EF according to the same rule that corresponding sides in congruent triangles are equal to each other. But according to what is given us in the question, side DE equals to x. So we can write down here that side DE equals to x, and from this equation x equals to DE equals to EF, we'll derive that side EF is also equals to x. Here, side EF is also equals to x. In the next step, I will present to you the law of cosines, and we will implement the law of cosines in this triangle, triangle EFC. So, what is the law of cosines? I've already mentioned it a couple times in the past, in the previous lectures. Actually, the law of cosines is true in any triangle, so I write down that in any triangle, so here we have triangle ABC that could be any triangle. This is triangle ABC. And we know that side AB of triangle ABC equals to A units in its length. And we also know that side AC equals to B units in its length. And the angle between side AB and side AC is theta. And we also know that side BC equals to C units in its length. Then, according to the law of cosines, the following equation is true, that C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. I repeat again, in triangle ABC that could be any triangle, C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. So we will implement the law of cosines in triangle EFC. This triangle, triangle EFC. So I copy triangle EFC in this page and we'll implement the law of cosines in this triangle, triangle EFC. This angle FCE equals to 30 degrees plus 30 degrees, that is 60 degrees. So, this is triangle EFC that I copied from the original drawing. And according to the law of cosines, we get that in triangle EFC, x squared equals to 4 squared plus 5 squared minus 2 times 4 times 5 cosine 60 degrees. So this equation is the implementation of the law of cosines in this triangle, triangle EFC. I repeat again, here x squared equals to 4 squared plus 5 squared minus 2 times 4 times 5 times cosine 60 degrees. Okay? So here x squared equals to 4 squared, that is 16, plus 5 squared, that is 25, minus 2 times 4 is minus 8, and minus 8 times 5 is minus 40. So it is minus 40 times cosine 60 degrees. And cosine 60 degrees equals to 1/2, so we substitute cosine 60 degrees by 1/2. So in total, this expression equals to minus 40 times 1/2. Okay, so we actually found out that x squared equals to 16 plus 25 is 41, and minus 40 over 2 is minus 20. So in conclusion, we found out that x squared equals to 41 minus 20. That is to say, x squared equals to 41 minus 20 is 21. So x squared equals to 21. Here we will take a root out of this equation and we get that x equals to the positive square root of 21 in terms of numbers. It is equal to 4.58 units. And the reason that x equals to the positive square root of 21 is because of the fact that x is a length, it must be a positive number. So here you can write down that x equals to either the positive square root of 21, or in terms of numbers, it is equal to 4.58 units. Okay, so we finished with the first question. In the next step, I will present to you the second question. So here in the drawing, we have a quarter circle. Inside this quarter circle, we have a circle and a semicircle that are touching each other at this point. This is the point of tendency between those two circular shapes. And we know that the radius of both the circle and the semicircle is equal to 2 units, and our mission is to find out the value of the area, the shaded area, or the value of the shaded area. Okay. We also know that this circle is tangent to the semicircle at this point. Okay, so first of all, because of the fact that this is a quarter circle, it means that this point is the center of the quarter circle, so we'll define this point as O, and point O is the center of the quarter circle. And also we know that this angle must be equal to 90 degrees. It is a right angle. It is true in any quarter circle. We define this point as point A. OA is the radius of the quarter circle. We define this point is point B. OB or BO is also the radius of the quarter circle. So you can write here that OA and OB, they are both the radii of the quarter circle. Okay? They are the radii of the quarter circle. Okay? So we define the point of tendency of tangent OA with this circle as point M. I'll repeat again that point M is the point of tendency of tangent OA with this circle. We'll define the center of this circle as P, and we'll define the center of this semicircle as point Q. Here point P is the center of the circle, point M is the point of the circle itself, therefore PM is the radius of this circle. And we also have rule number 1, according to rule number 1. A tangent to a circle is perpendicular to the radius drawn to its point of tendency. So your tangent AB is tangent to this circle is point M. Point M is the point of tendency, and we have the radius OM that is drawn to the point of tendency. Whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. So if AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees. We'll implement rule number 1 in our drawing. Here in our drawing, we have the radius PM that is drawn to the point of tendency, that is to say it is drawn to point M, that is the point of tendency of tangent OA in this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent OA will be perpendicular to the radius MP. So if OA is perpendicular to MP, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule number 1. In the next step, from the center of this circle, that is to say from point P, we will draw perpendicular on QO. So here, this angle equals to 90 degrees according to our construction, and this angle will be also equal to 90 degrees according to our construction. And we'll define the touching point of the perpendicular from point P and QO as L. L is the touching point of the perpendicular from point P and QO. Okay, so actually we created here quadrilateral LPOM that has 1, 2, 3 right angles. So I write it down. Quadrilateral LPOM is 1, 2, 3 right angles, and the sum of 3 right angles is 90 times 3 is 230 degrees, plus the size of the fourth angle, that is actually angle LPM. In total, the sum of those 4 angles must be equal to 360 degrees. Here, 270 degrees plus the size of angle LPM, it must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 60 degrees. So here we subtract 270 degrees from this equation, and we'll get that the missing angle LPM, is equal to 360 degrees minus 270 degrees. It is equal to 90 degrees. Okay. So we found out that this angle, it is a right angle, it is equal to 90 degrees. So we actually found out that all the angles inside quadrilateral LPOM are right angles. And any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we relate to quadrilateral LPOM as a rectangle. Okay. Why? Because it has 4 right angles. Okay. But we also know that the opposite sides of a rectangle are equal to each other. That is to say, in a rectangle LPOM, side PM equals to side LO. PM equals to LO. Here PM equals to LO according to the rule that the opposite sides of a rectangle are equal to each other. But we know that PM equals to 2 units, which is the radius of the circle. PM equals to 2 units, and from this equation 2 equals to PM equals to LO, we will conclude that LO is also equals to 2 units. LO is also equals to 2 units. So we can write here that LO equals to 2 units. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we will get that in rectangle LPOM, side LP must be equal to side OM. LP equals to OM. So if we define side LP as X, side LP equals to X according to our definition, then from this equation X equals to LP equals to OM, we will derive that side OM is also equals to X. Side OM equals to X. In the next step, we will focus at this point, that is the touching point between the circle and the quarter circle, and we will define the touching point of the quarter circle and the circle as point K. Actually, at point K, the circle and the quarter circle have an internal lunge between them. I repeat again, at point K, the circle and the quarter circle have an internal lunge between them. That is to say, they are touching each other internally at point K. And whenever you have two circular shapes that are touching each other internally, then the straight line that joins their centers together must pass through their touching point. Okay, I repeat again. Whenever you have two circular shapes that have an internal lunge between them, then the straight line that joins their centers together must pass through their touching point. So here, point O is the center of the quarter circle. Point P is the center of the circle. And the straight line that joins their centers together is the straight line OP. And this straight line OP, must pass through point K. That is their touching point. The straight line OP must pass through their touching point, that is actually point K. That is to say, OPK is one straight line. Okay, so you can write down that line segment OPK is one straight line. Or we can also say, in other words, that points O, P, and K, they are all located on the same straight line. Okay, so if OPK is a straight line, then OK is also a straight line. So OK is a straight line. And here, point O is the center of the quarter circle. Point K is the point on the quarter circle itself. This is exactly the definition of a radius. That is to say, line segment OK is the radius of the quarter circle. Okay, line segment OK is the radius of the quarter circle. We define the radius of the quarter circle as capital R. Therefore, we actually found out that OK, the straight line OK, equals to capital R. That is the radius of the quarter circle according to our definition. In addition, we know that point P is the center of the circle, point K is the point of the circle itself, therefore PK is the radius of the circle that is equal to 2 units according to what is given as the question. So we also found out that PK equals to 2 units. It is the radius of the circle. So in conclusion, we found out that OK equals to capital R, it is the radius of the quarter circle, and PK equals to 2 units, it is the radius of the circle. And what is the length of line segment PO? From the drawing, it is very easy to see that the length of line segment PO equals to PK. The length of line segment PO equals to KO minus KP. Okay, KO minus KP. Okay, PO equals to KO minus KP. Very simple. So PO equals to KO, and KO is the radius of the quarter circle that is equal to capital R minus KP. And we already found out that Kp equals to 2 units. So, in conclusion, we found out that the length of line segment PO equals to capital R minus 2. Okay? Here, line segment PO equals to capital R minus 2. In the next step, I will copy the right triangle OPM in a new page, and we will implement the Pythagoras theorem on this triangle OPM. Okay? So here the hypotenuse OP of triangle OPM is equal to capital R minus 2. OM equals to X and PM equals to 2 units. So this is the right triangle OPM that I copied from the original drawing. We will implement the Pythagoras theorem on this right triangle OPM. So here by PT is abbreviation for Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So the hypotenuse is OP, therefore the square of the hypotenuse is OP squared. And it must be equal to the sum of the squares of the perpendiculars, that is to say it must be equal to OM squared plus PM squared. Okay? OP equals to capital R minus 2, therefore OP squared equals to capital R minus 2 squared. And it is equal to OM squared. OM equals to X, so OM squared equals to X squared plus PM squared. PM equals to 2, so PM squared equals to 2 squared, that is 4. So in conclusion, we found out that R minus 2 squared equals to X squared plus 4. Here we open the brackets on this side of equation number 1. And we get that R minus 2 squared equals to R squared plus 2 squared, that is 4, minus 2 times R times 2 is minus 4R. And in the other side of the equation number 1 we have X squared plus 4. So here we have 4 on both sides of equation number 1. So 4 will get cancelled. What is left from equation number 1 after we cancelled 4? What is left is actually, in this side of the equation we have X squared, that is equal to R squared minus 4R. So according to equation number 1, we found out that X squared equals to R squared minus 4R. In the next step, we'll focus at this point, that is the touching point between the semicircle and the circle, or the point of tendency between the circle and the semicircle. And we'll define the touching point between those two circular shapes as point T. Again, point T is the touching point between the circle and the semicircle. Actually, at point T, those two circular shapes have an external notch between them. That is to say, at point T, the circle and the semicircle are touching each other externally. Okay? And whenever you have two circular shapes that have an external notch between them, then the straight line that joins their centers together must pass through their touching point. Here, the center of this circle is at point P. The center of this circle is at point, the center of this semicircle is point Q, and the straight line that joins their centers together is the straight line QP. And according to the rule that I mentioned, the straight line QP must pass for point T, that is their touching point. Here, the straight line QP must pass through point T, that is to say, QTP is one straight line. Okay, line segment QTP is one straight line. And we can also say, in other words, that points Q, T, and P, they are all located on the same straight line. Okay, so if QTP is a straight line, then QP is also a straight line. So I write down that QP is also a straight line. So, what is the length of the straight line QP? That is actually the distance between the two centers, the center of the semicircle and the center of the circle. Actually, the distance between the 2 points QP equals to QT plus TP. QT plus TP. QP equals to QT plus TP. Point Q is the center of the semicircle. Point T is the point of the semicircle itself. Therefore, QT, this is exactly the definition of a radius. QT is the radius of this semicircle that is equal to 2 units according to what is given as the question. Here, point P is the center of the circle. Point T is the point of the circle itself. Therefore, PT is the radius of this circle that is also equals to 2. So, in conclusion, we found out that QT equals to 2 units and TP also equals to 2 units. So, here, we get that QP equals to QT. We just right now found out that QT equals to 2 units. And we also found out that TP also equals to 2 units. So, in conclusion, QP equals to 2 plus 2, that is 4. Okay? So, here, QP equals to 4 units. Okay? And here, point Q is the center of the semicircle. Point B is the point of the semicircle itself. That is to say, QB is the radius of the semicircle that is equal to 2 units. And what is the length of line segment QL? Here, as I've already mentioned before, the length OB is defined as the radius of the quarter circle that is equal to capital R. Okay, here I've already written here OA and OB, they are the eye of the quarter circle. that is equal to capital R according to our definition. Okay, so what is the length of line segment QL? Yeah, the length of line segment QL from the drawing, it is very easy to see that the length of line segment QL equals to BO, that is the radius of the quarter circle, minus BQ, that is the radius of the semicircle, minus LO, that is equal to 2 units. I'll repeat again. The length of line segment QL equals to BO, that is the radius of the quarter circle, minus BQ, that is the radius of the semicircle. It is equals to BO, that is the radius of the quarter circle, minus BQ, that is the radius of the semicircle, minus LO, that is equal to 2 units. So you can write down that QL equals to BO, that is capital R, the radius of the quarter circle, minus BQ, that is equal to 2 units, minus LO, that is also equals to 2 units. So here, we found out that QL equals to capital R minus 2 minus 2, minus 2 minus 2 is minus 4. So in conclusion, we found out that the length of line segment QL equals to capital R minus 4. Okay. So you can write here that QL equals to capital R minus 4. In the next step, I will copy the right triangle QLP in a new page, and we will implement the Pythagoras theorem on this triangle QLP. Okay. We just right now found out that QL equals to capital R minus 4. And we have already found out that the hypotenuse QP equals to 4 units. And LP equals to X. So this is the right triangle QLP that I copied from the original drawing. So we will implement the Pythagoras theorem on this triangle QLP. So here, by PT is abbreviation for Pythagoras theorem. So according to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the circular perpendiculars. In this triangle QLP, the hypotenuse is QP, therefore the square of the hypotenuse is QP squared. And it must be equal to the sum of the circles of the perpendiculars, that is to say, it must be equal to QL squared plus LP squared. Repeat again, according to the Pythagoras theorem, QP square equals to QL square plus LP square. QP equals to 4, therefore QP square equals to 4 squared, that is 16. That is equal to QL square. QL equals to capital R minus 4, therefore QL square will be equal to capital R minus 4 square plus LP square. LP equals to X, so LP square will be equal to X square. So in conclusion, according to equation number 2, we found out that 16 equals to capital R minus 4 square plus X square. Here we will open the brackets on this side of equation number 2 and we get that according to equation number 2, 16 equals to capital R minus 4 equals to R square plus 4 squared, that is 16, minus 2 times R times 4 is minus 8R plus X square. So here we have 16 on both sides of equation number 2, so 16 will get cancelled. So what is left from equation number 2 after we cancelled 16? In this side of the equation nothing is left, so we have 0, that is equal to R square minus 8R plus X square. So here we will add 8R to this equation, equation number 2, and we will get that according to equation number 2, R equals to R square plus X square. So here we subtract R square from this equation, equation number 2, and we get that according to equation number 2, (8R minus R square) equals to X square. So according to equation number 2, we found out that X square equals to 8R minus R square, while according to equation number 1, we have already found out that X square equals to R square minus 4R. Okay, so we actually have two different expressions for X square. Therefore, we'll create equation number 3 that states that X square according to equation number 1 must be equal to X square according to equation number 2. Okay, X square according to equation number 1 must be equal to X square according to equation number 2. So here X square according to equation number 1 equals to R square minus 4R, and it must be equal to X square according to equation number 2, that is actually equals to 8R minus R square. So according to equation number 3, we found out that R square minus 4R equals to 8R minus R square. So here we will add R square to this equation, equation number 3, and we get that according to equation number 3, R square plus R square is 2R square minus 4R equals to 8R. Here we will add 4R to this equation, equation number 3, and we get that according to equation number 3, (2R square), 4R minus 4R is 0, so 2R square equals to 8R plus 4R, is 12r. In conclusion, we found out that according to equation number 3, 2r squared equals to 12r. Here we'll divide this equation number 3 by 2. And we get that 2r squared over 2 is r squared. That is equal to 12r over 2 is 6r. So in conclusion, we found out that according to equation number 3, r squared equals to 6r. Here we'll subtract 6r from this equation number 3, and we'll get that according to equation number 3, r squared minus 6r equals to 0. So here we'll take r as a common factor from this equation number 3, and we'll get that r is a common factor. So what is left from r squared after we took from it r as a common factor? What is left is actually r. And what is left from minus 6r after we took from it r as a common factor? What is left is actually minus 6. So in conclusion, we found out that r times r minus 6 equals to 0. So here we have two solutions that are possible for r. The first solution for r is that r equals to 0, but because of the fact that r is the length of the radius of the quarter circle, r is a length, it must be a positive number, it cannot be equal to 0. So we cancel this solution, and so we left only with the second solution, that r minus 6 equals to 0. Here we will add 6 to this equation, and we get that r, the radius of the quarter circle, equals to 6 units. So, and we know that the area of any quarter circle equals to the area of the circle over 4. That is to say, it is equal to pi r squared over 4 when r equals to 6 units. And what is the area, what is the value of the shaded area here? From the drawing, it is very easy to see that the value of the shaded area equals to the area of the quarter circle minus the area of the circle minus the area of the semicircle. So write it down again, that the value of the shaded area equals to the area of the quarter circle minus the area of the circle minus the area of the semicircle. I'll repeat again. The value of the shaded area equals to the area of the quarter circle minus the area of the circle minus the area of the semicircle. Okay, so here the value of the shaded area equals to the area of the quarter circle, that is actually equals to pi r squared over 4 minus the area of the circle. The area of the circle is pi r squared and the radius is 2, so it is pi 2 squared minus the area of the semicircle. The area of the semicircle equal to the area of the circle over 2, that is to say it is equal to pi r squared over 2, and r equals to 2, so it is pi 2 squared over 2. So here I found out that the radius of the quarter circle is 6, so r is 6, therefore r squared is 6 squared, that is 36. So in total this expression equals to 36 pi over 4. This is the area of the quarter circle. Minus 2 square is 4, and 4 times pi is 4 pi, so it is minus 4 pi. Minus pi to square over 2, 2 square is 4, and 4 over 2 is 2, and 2 times pi is 2 pi. So the area of the semicircle is 2 pi. So here 36 over 4 is 9, and 9 times pi is 9 pi. So in conclusion, the area of the quarter circle is 9 pi. So it is actually 9 pi minus 4 pi minus 2 pi. 9 pi minus 4 pi is 5 pi, and 5 pi minus 2 pi is 3 pi. So in conclusion, we found out that the value of the shaded area equals to either 3 pi square units, or in terms of numbers, it is equal to 9.42 square units. Okay? I repeat again, the value of this shaded area equals to either 3 pi square units, or in terms of numbers, it is equal to 9.42 square units. So in the next step, I will summarize the lecture. We'll start with the first question, of course. In the drawing, we have triangle ABC. Note that angle ABC equals to 30 degrees, angle ACB equals to 30 degrees, angle DAE equals to 60 degrees, line segment BD equals to 5 units, line segment EC equals to 4 units, and our mission is to find out the value of line segment DE that is equal to X. So first of all, we focus on triangle ABC. And you know that those two angles are equal to each other, they are both equal to 30 degrees. So in the right triangle ABC, angle ABC equals to angle ACB, and they are both equal to 30 degrees, therefore they are equal to each other. And according to the rule that in front of equal angles in the triangle there are equal sides, we get that in triangle ABC, side AB equals to side AC because of the fact that those two sides are located between the equal angles that are angle ABC and angle ACB. So here, side AB equals to side AC. Okay? And we also know that the sum of the angles in any triangle is equal to 180 degrees, and especially the sum of the angles in triangle ABC must be equal to 180 degrees. So we define angle BAD as alpha, and angle EAC as beta, and the sum of the angles in triangle ABC equals to 180 degrees. That is to say, this angle is equal to 30 degrees plus this angle that is equal to 30 degrees also, plus this angle that is equal to alpha, plus this angle that is equal to 60 degrees, plus this angle that is equal to beta. In total, the sum of those all angles must be equal to 180 degrees. Okay? So here we have 30 degrees plus 30 degrees is 60 degrees, and 60 degrees plus 60 degrees is 120 degrees. So in conclusion, we found out that 120 degrees plus alpha plus beta equals to 180 degrees. We subtracted 120 degrees from this equation, and we found out that alpha plus beta equals to 180 degrees minus 120 degrees is 60 degrees. Then we did the construction. We did two constructions actually. From point A, we draw a straight line in such a way that the angle between the straight line and side AC of triangle ABC is equal to alpha. So this angle equals to alpha according to our definition. And the second construction that we did is from point D, we draw a straight line in such a way that the angle between the straight line and side AC is 30 degrees. So this angle equals to 30 degrees according to our construction. So in this way we created triangle AFC, and we proved that the new triangle that we created, that is triangle AFC, can go into triangle ABD. Repeat again, we proved that triangle ABD can go into triangle AFC. So why those two triangles can go into each other? First of all, those two angles are both equal to alpha, therefore they are equal to each other. Here, angle BAD equals to angle CAF equals to alpha. In addition, we have already found out that side AB equals to side AC. Okay, side AB equals to side AC. And finally, those two angles are both equal to 30 degrees, therefore they are equal to each other. Yeah. Angle ABD equals to angle ACF. They are both equal to 30 degrees, therefore they are equal to each other. So we actually proved that triangle ABD is congruent to triangle AFC according to angle side angle rule. I'll explain what I mean. Here we have in this triangle ABD, we have those two angles that are alpha and 30 degrees, and the side that is attached to those two angles, that is actually side AB, that correspondingly congruent to those two angles that are alpha and 30 degrees, and the side that attached to those two angles, that is side AC and triangle ACF. Therefore, those two triangles can go into each other according to angle side angle rule. And from the fact that those two triangles can go into each other, we conclude two things. The first thing that we conclude that side BD equals to side FC. Side BD equals to side FC according to the rule that corresponding sides in congruent triangles are equal to each other. Those two triangles can go into each other, therefore the two corresponding sides, that is to say BD and FC, must be also equal to each other. But BD equals to 5 units according to what is given as the question. So I can write here that BD equals to 5 units, and from this equation 5 equals to BD equals to FC, we derive that FC is also equals to 5 units. Here, FC equals to 5 units. And the second thing that we conclude from the fact that those two triangles can go into each other is the side AD equals to side AF. Side AD equals to side AF according to the sum rule that corresponding sides in congruent triangles are equal to each other. So if we define side AD as A, side AD equals to A according to our definition, then from this equation A equals to AD equals to AF, we will derive that side AF is also equals to A. Here side AF equals to A. In the next step, we joined points E and F by straight line, and we proved that the green triangle is congruent to the orange triangle. So why those two triangles can go into each other? First of all, side AD equals to side AF equals to A. Side AD equals to side AF equals to A. In addition, those two angles are both equal to 60 degrees because we know that alpha plus beta equals to 60 degrees, and therefore they are equal to each other. Here, angle DAE equals to angle EAF equals to 60 degrees. And finally, side AE is a common side that belongs to both triangles, so actually this side is equals to itself. It's a common side. AE equals to AE is a common side that belongs to both triangles. So we actually proved that the green triangle, triangle ADE, can go into the orange triangle, triangle AEF, according to side angle side rule. I'll explain what I mean. Here, those two sides and the angle that is included between those two sides, that is to say this angle, in the green triangle can go into correspondingly to those two sides and the angle that is included between those two sides in the orange triangle. Therefore, those two triangles can go into each other according to side angle side rule. And from the fact that the green triangles can go into the orange triangle, we conclude that side DE equals to side EF. Here, side DE equals to side EF, according to the same rule that corresponding sides in congruent triangles are equal to each other. But we have already found out that side DE equals, according to what is given as the question, side DE equals to X. According to what is given as the question, side D equals to X, and from this equation X equals to D equals to EF, we will derive that EF is also equals to X. Here, EF is also equals to x. Okay. In the next step, I presented to you the law of cosines, and we implemented the law of cosines in this triangle EFC. So what is the law of cosines? The law of cosines is through in any triangle. So if we have here triangle ABC, that could be any triangle, we know that the length of side AB is A units, the length of side AC is B units, and the angle between side AB and side AC is theta, and the length of side BC equals to C units. Then in this triangle ABC, the following equation is true, that C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. Again, C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. And we actually implemented the law of cosines in this triangle EFC. Here, angle ECF equals to 30 degrees plus 30 degrees, that is 60 degrees. Side DC equals to 4 units, side DC equals to 5 units, and side EF equals to x, that is the line segment that we are looking for. So according to the law of cosines, if we implement the law of cosines in this triangle EFC, we'll get that x squared equals to 4 squared plus 5 squared minus 2 times 4 times 5 times cosine 60 degrees. Again, x squared equals to 4 squared plus 5 squared minus 2 times 4 times 5 times cosine 60 degrees. So here 4 squared is 16, 5 squared is 25, and minus 2 times 4 is minus 8, and minus 8 times 5 is minus 40, and cosine 60 degrees equals to 1 half, so we substituted cosine 60 degrees by 1 half, and in conclusion, in total this expression equals to minus 40 times 1 half. So in conclusion, we found out that 16 plus 25 minus 40 times 1 half equals to x squared. Then 16 plus 25 is 41, so we found out that x squared equals to 41, and minus 40 over 2 is minus 20. So in conclusion, we found out that x squared equals to 41 minus 20. 41 minus 20 is 21, so we found out that x squared equals to 21. We took a root out of this equation and found out that x equals to the square root of 21, the positive square root of 21. Or in terms of numbers, it is equal to 4.58 units. I repeat again, the reason that we will take only the positive square root of 21 because of the fact that x is a length. As a length, x must be a positive number. So in conclusion, we found out that the length of line segment DE that is equal to x, it is either equals to the positive square root of 21, or in terms of numbers, it is equal to 4.58 units. We finished with the first question, and then I presented to you the second question. In the drawing, we have a quarter circle. Inside this quarter circle, we have a circle and a semicircle that are tangent to each other at this point T. And we also know that the circle is tangent to the quarter circle at point K. And we also know that both the radii of the circle and the semicircle are equal to 2 units, and our mission is to find out the value of the shaded area. So first of all, because of the fact that this is a quarter circle, it means that this point must be the center of the quarter circle. That is to say, point O is the center of the quarter circle, and this angle QOA equals to 90 degrees. And we also know that OA and BO are both the radii of the quarter circle. Okay, so we have here tangent OA is tangent to this circle is point M. Point M is the point of tendency, and according to rule number 1, a tangent to a circle is perpendicular to the radius going to its point of tendency. So here we have tangent AB, that is tangent to this circle is point M. M is the point of tendency, and we have the radius OM that is drawn to the point of tendency. And whenever we have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. So if AB is perpendicular to MO, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees. We actually can implement rule number 1 in our drawing, because in our drawing we have the radius PM that is drawn to the point of tendency, that is to say it is drawn to point M, that is the point of tendency of tangent OA with this circle. Whenever we have a radius that is drawn to the point of tendency, then tangent OA will be perpendicular to the radius MP. So if OA is perpendicular to MP, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule number 1. In the next step, from the center of this circle that is actually point P, we draw perpendicular on QO. So this angle equals to 90 degrees and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point P and QO as L. Okay, actually we created here quadrilateral LPOM. Inside quadrilateral LPOM we have 1, 2, 3 right angles. I'll repeat again, inside quadrilateral LPOM we have 3 right angles, and the sum of 3 right angles is 90 times 3 is 270 degrees. So 270 degrees plus the size of the fourth angle that is actually LPM. In total, they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Here we subtracted 270 degrees from this equation and we found out that the missing angle LPM, this angle, it is equal to 360 degrees minus 90 degrees. 360 degrees minus 90 degrees, 360 degrees minus 270 degrees equals to 90 degrees. So we found out that the missing angle, this angle, equals to 90 degrees, it is a right angle. Therefore, actually, in quadrilateral LPOM, we have 4 right angles, and any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. Okay, so we relate to quadrilateral LPOM as a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. So the opposite sides of a rectangle LPOM must be equal to each other. That is to say, side PM must be equal to side LO. PM equals to LO. But we know that PM equals to 2 units. So, and for this equation 2 equals to PM equals to LO, we will derive that LO is also equals to 2 units. Here, LO also equals to 2 units. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we get that LP equals to OM. LP equals to OM, so if we define side LP as X, here LP equals to X, then from this equation X equals to LP equals to OM, we will derive that OM also equals to X. Here OM is also equals to X. Then we focus at point K. Point K is the touching point between the circle and the quarter circle. So actually at point K, this circle and the quarter circle have an internal notch between them. And whenever you have 2 circular shapes that have an internal notch between them, then the straight line that joins their centers together must pass through their touching point. I'll repeat again, whenever you have 2 circular shapes with an internal notch between them, then the straight line that joins their centers together must pass through their touching point. In this case, the center of the quarter circle is point O. The center of the circle is at point P, and the straight line that joins their centers together is PO. And according to the rule that I mentioned, this straight line PO must pass from point K, that is their touching point. Or in other words, KPO is one straight line. Okay, KPO is one straight line, or we can actually say that points K, P, and O are all located on the same straight line. So if KPO is a straight line, then KO must be also a straight line. So here OK or KO is a straight line. But point O is the center of the quarter circle. Point K is the point on the quarter circle itself. That is to say, OK is the radius of this quarter circle. Here OK is the radius of the quarter circle. And we define the radius of the quarter circle as capital R. Therefore, OK equals to capital R. Likewise, we know that point P is the center of the circle. Point K is the point on the circle itself. Therefore, PK is the radius of this circle that is equal to 2 units according to what is given us the question. So in conclusion, we found out that OK equals to capital R. It is the radius of the quarter circle. While PK equals to 2 units, it is the radius of the circle. And what is the length of line segment OP? From the drawing it is very easy to see that OP equals to OK minus KP. Okay, or PO equals to KO minus KP. Okay, PO equals to KO minus KP. Okay, PO equals to KO minus KP. So PO equals to KO. KO equals to capital R. And KP equals to 2. So in conclusion, we found out that the length of line segment PO equals to capital R minus 2. Yeah, this line segment PO equals to capital R minus 2. So I copied the right triangle OPM in a new page and we implemented the Pythagoras theorem on this right triangle OPM. This is the right triangle OPM that I copied from the original drawing. We know that the hypotenuse OP equals to capital R minus 2, PM equals to 2, and OM equals to X. So according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is PO, so for the square of the hypotenuse is PO square or OP square, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to OM square plus PM square. So OP equals to capital R minus 2, so OP square is capital R minus 2 square. That is equal to OM square. OM is X, so OM square is X square plus PM square. PM is 2, so PM square is 2 square, that is 4. So in conclusion, we found out that R minus 2 square equals to X square plus 4 according to equation number 1. We open the brackets on this side of equation number 1. We found out that R minus 2 square equals to R square plus 2 square, that is 4, minus 2 times R times 2, that is minus 4R. That is equal to X square plus 4. Here we have 4 on both sides of the equation, so 4 will get cancelled. So in conclusion, we found out that according to equation number 1, X square equals to R square minus 4R. Then we focus at this point. This is actually the touching point between the semicircle and the circle. So we define the touching point between the semicircle and the circle as T. At point T, the circle and the semicircle have an external between them. That is to say, they are touching each other externally at point T. And whenever you have two circular shapes that are touching each other externally, then the straight line that joins their centers together must pass through their touching point. I repeat again, whenever you have two circular shapes that have an external between them, then the straight line that joins their centers together must pass through their touching point. Here, point P is the center of the circle, point Q is the center of the semicircle. And the straight line that joins their centers together is QP, and this straight line QP, according to the rule that I mentioned, this straight line QP must pass through their touching point, that is point T. That is to say, QTP is one straight line. Okay, QTP is one straight line. Or we can also say in other words, that points Q, T, and P, they are all located on the same straight line. So if QTP is a straight line, then QP is also a straight line. So QP is a straight line. And what is the length of the straight line QP? From the drawing, it is very easy to see that QP equals to QT plus TP. Okay, QP equals to QT plus TP. And Q is the center of the semicircle. T is the point on the semicircle itself, that is to say QT is the radius of the semicircle, that is equal to 2 units. Likewise, point P is the center of the circle. Point T is the point on the circle itself. Therefore, PT is the radius of this circle, that is also equals to 2 units. So in conclusion, we found out that QT equals to 2 units and TP also equals to 2 units. Okay? And we know that QP equals to QT plus TP. We found out that QT equals to 2 units and TP also equals to 2 units. So in conclusion, we found out that QP equals to 2 plus 2. 2 plus 2 is 4, so in conclusion, we found out that the length of the straight line QP equals to 4 units. Okay, QP equals to 4 units. This line segment QP equals to 4 units. Then here, point Q is the center of the semicircle. Point B is the point of the semicircle itself, that is to say QB is the radius of this semicircle, that is equals to 2 units. Then we found out the length of line segment QL. It is very easy to see that the length of line segment QL equals to BO, that is capital R, it is the radius of the quarter circle, minus BQ, that is the radius of the semicircle, minus LO. I'll repeat again. The length of line segment QL equals to BO, that is the radius of the quarter circle, minus BQ, that is the radius of the semicircle, minus LO, that is equal to 2 units. So here QL equals to BO, that is the radius of the quarter circle, that is equal to capital R, minus BQ, that is the radius of the semicircle, that is equal to 2, minus LO, that is also equals to 2. So in conclusion, we found out that QL equals to capital R minus 2 minus 2 minus 2 minus 2 is minus 4. So in conclusion, we found out that QL equals to capital R minus 4. So here we can write down that QL equals to capital R minus 4. In the next step, I copied the right triangle QLP in a new page and implemented the Pythagoras theorem on this triangle QLP. So this is the right triangle QLP that I copied from the original drawing. We just right now found out that QL equals to capital R minus 4. This again equals to 90 degrees according to our construction. Side LP equals to X, and we have already found out that the hypotenuse QP equals to 4 units. Then we implemented the Pythagoras theorem on this triangle QLP. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The square of the hypotenuse is QP square, and it must be equal to the sum of the squares of the perpendiculars, that is to say it must be equal to QL square plus LP square. QP equals to 4, so QP square is 4 squared, that is 16. QL equals to X, so QL square is X squared. Now QL equals to capital R minus 4, therefore QL square is capital R minus 4 square, plus LP square. LP equals to X, so LP square equals to X square. So in conclusion, we found out that according to equation number 2, 16 equals to R minus 4 square plus X square. So here we open the brackets on this side of equation number 2 and found out that according to equation number 2, 16 equals to R minus 4 square. R minus 4 square equals to R square plus 4 square, that is 16, minus 2 times R times 4, that is minus R plus X square. So here we have 16 on both sides of the equation, so 16 will get cancelled. What is left from equation number 2 after we cancelled 16? In this side of the equation, nothing is left, so we have 0. On the other side of the equation, we have left with R square minus 8R plus X square. So here we added 8R to this equation. Actually we added 8R to this equation number 2, and we found out that according to equation number 2, 0 plus 8R is 8R. In the other side of the equation, we have R square plus X square. So according to equation number 2, 8r equals to r squared plus x squared. Here we subtracted r squared from this equation number 2, and found out that according to equation number 2, x squared equals to 8r minus r squared. Well, according to equation number 1, we already found out that x squared equals to r squared minus 4r. So we have two different expressions for x squared. Therefore, we created equation number 3 that states that x squared according to equation number 1 must be equal to x squared according to equation number 2. X squared according to equation number 1 is r squared minus 4r, while x squared according to equation number 2 is 8r minus 4r, 8r minus r squared. And those two expressions are equal to each other because they are both equal to x squared. So here we added r squared to this equation number 3, and found out that r squared plus r squared is 2r squared minus 4r equals to 8r. Here we added 4r to this equation number 3, and found out that 2r squared, 4r minus 4r is 0, and it is equal to 8r plus 4r is 12r. So in conclusion, we found out that 2r squared equals to 12r. Here we divided this equation number 3 by 2, and we found out that 2r squared over 2 is r squared, and 12r over 2 is 6r. So in conclusion, we found out that according to equation number 3, r squared equals to 6r. Here we subtracted 6r from this equation number 3, and we found out that according to equation number 3, r squared minus 6r equals to 0. Here we took r as a common factor from this expression, and so here r is a common factor. What is left from r squared after we took from it r as a common factor? What is left is actually r, and what is left from minus 6r after we took from it r as a common factor? What is left is actually minus 6. So in conclusion, we found out that according to equation number 3, r times r minus 6 equals to 0. Okay, so here we will have two solutions that are possible for r. The first solution for r is that r equals to 0. But because of the fact that r is the length of the radius of the quarter circle, r is a length, it must be a positive number. It can never be equal to 0, so we cancel this solution, and we left only with the second solution that r minus 6 equals to 0. Here r minus 6 equals to 0, so we added 6 to this equation, and we found out that r equals to 6 units. So we actually found out that the radius of this quarter circle, it is equal to 6 units. Now it is very easy to find out the area of the quarter circle. It will be equal to the area of the circle that is pi r squared over 4. And we know that r equals to 6. And what is the area, what is the value of the shaded area? The value of the shaded area equals to the area of the quarter circle minus the area of the circle minus the area of the semicircle. And repeat again, the area, the value of the shaded area equals to the area of the quarter circle minus the area of the circle minus the area of the semicircle. I already mentioned that the area of the quarter circle will be equal to pi r squared over 4 when r equals to 6. The area of the circle is pi r squared and r equals to 2, so it is pi 2 squared, while the area of the semicircle equals to the area of the circle over 2, that is pi r squared over 2, and r equals to 2, so it is pi 2 squared over 2. R equals to 6, so r squared is 6 squared, that is 36, so in total this expression equals to 36 pi over 4. This is the area of the quarter circle minus the area of the circle, that is pi 2 squared. 2 squared is 4, and 4 times pi is 4 pi. So 4 pi is the area of the circle minus the area of the semicircle, that is pi 2 squared over 2. 2 squared is 4, and 4 over 2 is 2. So in total this expression equals to 2 pi. And here 36 over 4 is 9, so in total this expression equals to 9 pi. So we actually found out that the value of the shaded area equals to 9 pi minus 4 pi is 5 pi, and 5 pi minus 2 pi is 3 pi. So in conclusion, we found out that the value of the shaded area equals to either 3 pi square units, or in terms of numbers, it is equal to 9.42 square units. I repeat again, the value of this shaded area equals to either 3 pi square units, or in terms of numbers, it is equal to 9.42 square units. Okay, thank you very much.